For the past few years, those of us in the AI community, we've been more than just engineers or researchers, haven't we? We've really been architects. We've been drafting the blueprints and laying the foundations for, well, a whole new world. So today I want to frame our progress not as just a series of disconnected breakthroughs, but as the deliberate construction of a vast, sprawling digital metropolis.
So let's take a tour of this city we're building. We're going to start with the foundational infrastructure, our massive skyscrapers. Then we'll look at the new zoning laws that are bringing some much-needed order. After that, we'll check out the modular interior designs we're using to upgrade everything and meet the city's very first citizens, our active agents. We'll even peek into how this metropolis actually thinks and what fuels its intelligence, the city's library.
But before we lay the first brick, it's worth remembering what started this whole crazy project. Way back in 1985, Hodgkin defined our goals so perfectly: to create machines with minds. I mean, that's been the guiding star for this entire architectural endeavor. Okay, so our story begins in what I like to call the Skyscraper Era. The mission was simple: build bigger. The large language models were our magnificent towers, each one more massive and more complex than the last. We were in a flat-out race to the clouds, totally focused on just scaling up our foundational infrastructure. But, as any architect will tell you, just building big, well, that introduces some pretty fundamental challenges. And that led us straight into the classic bias-variance trade-off. See, a model with high bias is like a city with a super rigid, oversimplified plan. It's orderly, sure, but it completely misses the complex, messy patterns of how people actually live. But on the other hand, a model with high variance, that's a chaotic city with no plan at all. It's building new structures in response to every random gust of wind, mistaking all that noise for a real signal. The real challenge was, and still is, finding that perfect sweet spot between a rigid blueprint and just total chaos. So we had our skyscrapers, but they were unpredictable. We desperately needed to bring some order to the city. We needed zoning laws. And this, right here, is the challenge of alignment: making sure our incredibly powerful models operate safely and predictably for the good of all the future citizens. Our first attempt at zoning was reinforcement learning from human feedback, or RLHF. Now, you can think of this as a human inspection committee. Seriously, for every single modification, we had to bring in human evaluators to approve or deny the changes. It worked, but man, was it slow and expensive and just incredibly complex. The real breakthrough has been the shift to direct preference optimization, or DPO. DPO is like an automated self-enforcing building code. It's beautiful. It completely reframes the entire problem, turning it from this complex reward modeling headache into a simple classification loss. It's faster, it's cheaper, and it's a whole lot more stable. So how does DPO pull this off? Well, the magic is in the math, specifically a concept called Divergence. Now, forget the complicated formula for a second. Just think of it as a way to measure the distance between two different sets of plans for our city. It lets our automated building code gently nudge the model's development in the right direction, aligning it with what we want, all without needing that slow, expensive human committee for every single decision. It's a game changer. All right, so our skyscrapers are built and our zoning laws are in place. What's next? Specialization. How do we adapt these massive, general-purpose buildings for specific tasks? We couldn't afford to rebuild a whole skyscraper every time we needed a new function. No way. We needed a way to do efficient, modular renovations. And this table just shows how incredibly efficient these new methods are. Full fine-tuning means training all 100% of the model's parameters. That's literally rebuilding the entire skyscraper. But these parameter-efficient fine-tuning methods, or PEFT methods, are something else entirely. Low-rank adaptation, or LoRA, only trains about 0.1% of the parameters. That's like freezing the building's foundation and structure and just adding a new specialized floor. And then you have methods like II3, which are even more efficient, training just 0.01% of parameters. That's like installing smart systems throughout the building without even touching the walls. And we can squeeze even more efficiency out of this through a process called quantization. Basically, it reduces the precision of the model's numbers, say from 16-bit down to 4-bit, which makes it a lot smaller. When you combine that with LoRA, you get QLoRA, and this just dramatically slashes the memory footprint. What does that mean for us? It means we can now perform major renovations on a 65 billion parameter skyscraper using just a single GPU. It's a profound democratization of this tech. So up to this point, our metropolis has been a city of these magnificent but ultimately static structures. But now everything changes. This city is coming to life. It's being populated by its first intelligent citizens, what we call agents.
And the shift here it's monumental. Early AI was like a simple reflex agent, basically a static information kiosk. It could see the world right now and react based on a simple rule. But modern agents, they're model-based. They have an internal state, a memory. They don't just understand what the world is like now, they understand how it evolves and how their own actions will change it. They're not passive information providers anymore. They're active city workers with tools, capable of actually doing things.
So, if our city now has active citizens, the next logical question is, how do they think? And this brings us to one of the most exciting frontiers right now, inference-time computation. Our agents are actually developing an internal thought process, an inner monologue. Before an agent responds to you, it engages in what we call a chain of thought. First, it deconstructs your request to find the core problem. Then, it formulates a multi-step plan, kind of like how you'd work through a logic puzzle. And this part is crucial. It then verifies its own internal plan, checking it for flaws before it generates a single word of output. Only then does it execute the plan and deliver a final, reasoned answer. Our city's citizens don't just talk, they think.
But for our citizens to think effectively, they need access to high-quality information. And this brings us to a major debate in our field, a sort of AI war. For years, we thought the height of our skyscrapers was all that mattered. But we're realizing that what's inside them, the city's library, its knowledge base, is actually way more important. And this slide just perfectly illustrates the power of data quality. Look at this. You can have a massive 70 billion parameter model that you've trained on let's call it a messy library of unfiltered web data. And sure, it might score 75% on a key benchmark, but then you take a much smaller, more agile 7 billion parameter model, a small language model or SLM, and you train it on a perfect library of high-quality, curated, maybe even synthetic data. What happens? It blows the bigger model out of the water, scoring 85%. It's incredible. The quality of the knowledge is just crushing the raw scale of the infrastructure. We're finally learning that a world-class librarian is more valuable than an extra 100 floors on a skyscraper.
So where is this all going? Well, our focus is shifting. For decades, the goal was the Turing test, building machines that could perfectly mimic human thought. We're moving beyond that now. We are entering what I'd call a post-Turing reality. In this new reality, the goal isn't to create a competing intelligence, but a collaborative partner. This isn't about replacing human intellect, it's about augmenting it. This human-in-the-loop ecosystem is where we're going to tackle the world's most wicked problems. Imagine an AI partner that helps us discover new materials overnight by analyzing millions of molecular combinations, or one that sifts through petabytes of climate data to build better models. It's about a true cognitive partnership to solve challenges that have always been just out of our reach. So here we are. Our digital metropolis is built. The infrastructure is in place, the zoning laws are working, and intelligent citizens are walking its digital streets. We spent decades asking, can they think? That question has been answered. The real question for our generation, the one that's going to define everything that comes next, is this: how will we think with them?